A very important class of sequences involves sums or infinite sums of other sequences. Now we don't really take a full infinite sum, but suppose an is a sequence of real numbers. We define a new sequence xn by setting xn equal to the sum on the index k equals 1 to n of the terms ak. And so this is a1 plus a2 plus all the way up to an. Then if xn has a limit, we say that the infinite series sum k equals 1 to infinity of ak equals the limit as n approaches infinity of xn, which is by definition the limit as n approaches infinity, the sum k equals 1 to n of ak. And we say that it converges. The quantities sum ak, k equals 1 to n, are called the partial sums of this infinite series. If the partial sums do not have a limit, we say that the infinite series diverges. Note that this is in contrast to the case of sequences where divergence means that we get a positive infinity or negative infinity, and if it oscillates, then the limit does not exist. Instead, we'll just characterize this behavior for series as divergence. So just as with sequences, a very important class of series involves the geometric series. And the reason these are so important is that we can actually calculate their limits when they are in fact convergent. So a geometric series, well, the partial sums, Sn, are of the form sum from k equals 1 to n, a times some real number r to the kth power. So in particular, the inside terms are just a geometric sequence, and we know how those converge, but how do we examine the convergence of this object? Well, with a little algebra, we can see that we can distribute out a from all the terms, and then we have just r to the k. Well, it turns out there's a somewhat nice formula for r to the k. And so one way to see that nice formula is by noting that if I multiply by r to the k, 1 minus r over 1 minus r, well, of course I'm going to get 1 minus r in the denominator, so I can just bring that out immediately. But what happens inside this sum? Well, inside the sum, I'm going to have sum k equals 1 to n rk minus rk plus 1. So this is a very interesting insight. So it benefits us to expand this out. So let's look at what happens here. So what is the k equals 1 term? Well, I have r, and then I'll have minus r1 plus 1, which is r squared. That's the k equals 1 term. How about the k is equal to 2 term? When k is equal to 2, well, I get an r squared, and then I have 2 plus 1 is 3. So I have a minus r to the third power. What about the k equals 3 term? Well, now I have r3 minus, and I again see the pattern, r4. And this continues. This continues until I look at the term with index k is equal to n, and that'll give me r to the n, and then I'll have r to the n plus 1 at the end. But here's what we notice. We notice that successive terms here will cancel out. This will cancel with this. This will cancel with this. This will cancel with the fourth entry, so on and so forth, until this eventually gets canceled, and we're left with r n plus 1. So this will be equal to a1 minus r times r minus r n plus 1, which is equal to a r over 1 minus r times r times 1 minus r to the n. So that's really nice that we kind of lucked out and we have a nice formula for what the nth term looks like. And in particular, we have this constant term that multiplies something that is 1 minus r to the power n. And so now we can start to establish the convergence behavior. On a brief note, this behavior, where these terms cancel out, we'll talk about it again, but this is our first glancing blow with a phenomenon called telescoping. Telescoping is where successive powers cancel out, and I can establish what the sum looks like in a much simpler fashion. Okay, so now we have the sum. This is Sn. So let's write it down. Sn is equal to a times r over 1 minus r, and then I have this term 1 minus r to the n. That's the expression that we have for Sn. Well, this looks awfully a lot like a geometric sequence, and we know the convergence behavior. In particular, if r is greater than 1, then what has to happen? Well, if r is greater than 1, this has to blow up. The r to the n term blows up, and ultimately I'm going to have 1 minus something really large, and this will diverge. In particular, this limit diverges. What about if r is equal to 1? Well, if r is equal to 1, this doesn't even make sense, but if we go back to our formula, well, I have a times r to the kth power. Now, I'll just have a for each of those, and so I established that Sn is just going to be equal to a times n, which diverges as well. But now, if minus 1 is less than r is less than 1, the nice thing is that Sn equal a r over 1 minus r, 1 minus rn, converges. In particular, this r to the n term is going to 0. And we know that the limit, therefore, as n approaches infinity of these partial sums, is going to be just a r over 1 minus r. This is an important formula to remember for geometric series. And if, similarly, if r is less than minus 1, Sn diverges. So now it's good to have an example where we use actual numbers. So in this example, let's let a equal 3 and say r is equal to 1/2. And we're going to set Sn equal to the sum from k equals 0 to n, a r to the k. Now your quick temptation might be, and this is bad or dangerous reasoning, your quick temptation might be to say, oh, well, just use the formula. And then you write limit as n approaches infinity of sum k equals 0 to n, a r to the k is equal to, well, it's just a r over 1 minus r, right? So you just plug things in. You get 3 times 1/2 over 1 minus 1/2. Well, that'll be 1/2 over ultimately 1/2, and so I just get 3. But this is wrong. This is wrong. Why is that? Because our formula was in terms of k equals 1 to n. This index is k equals 0 to n. And so we have to be slightly more careful. Well, how do we get k equals 1 to n? Well, we can change things up just a little bit by doing a little bit of algebra. So what if we multiply by r over r? So now I'm going to have 1 over r sum k equals 0 to n, and then I have a r to the k plus 1. And now I can re-index everything that is happening here. And so I have 1 over r sum k equals 0 to n plus 1, a to the rk. Sorry, this should be k is equal to 1 in the re-indexing. And so now I've re-indexed, and so I have something that abides by my formula, but I have a 1 over r sitting out here. So now I know the limit of this thing. So now limit as n approaches infinity of Sn will be equal to r times the limit as n approaches infinity of the sum that I know, k equals 1, and I can just leave an n there because I can re-index ar to the k. And now I can apply my formula because my formula was with respect to the index k equals 1 starting. And so now I have r times a, r over 1, sorry, it should be 1 over r. 1 over r is what we carried over. R over 1 minus r. So now I can plug in my numbers. So this is equal to 1 over 1/2. 3 times 1 over 1/2. I can use that formula again. In the denominator, I'll get a 1 over 1/2. And so now what happens? Well, the 1/2s will cancel, but now I get a 2 in the numerator, and so this is ultimately actually equal to 6. So we really messed up if we did this original calculation. And why is that? Well, this original calculation was right if my index started at k equals 1. And so that means that I discounted that very first term. And what's the very first term? Well, it's 3 times 1/2 to the 0th power. Another way I could have gone about this is, well, sum k equals 0 to n. Well, I can just extract out the k equals 0 term. So I have ar to the 0 plus sum k equals 1 to n now, ar to the k. And so that would be 3, because r to the 0 will always just be a. And then I have plus 3 sum k equals 1 to n of 1/2 to the kth power. This is just another way to get at this number. And so I know that the limit of this thing will again be this ratio of 1/2 over 1 minus 1/2. And so this will approach still 6 as n approaches infinity. And this is just two ways to kind of go about things. You can do algebraic manipulations to these partial sums in any way you want in order to finally apply formulas and calculate the limit. Let's revisit telescoping series. Now we've seen some telescoping behavior that allows us to essentially calculate a limit, and so the geometric series is a really nice class of examples, but there are a few more that we can consider. So, for example, how about the sum from k equals 1 to infinity of 1 over 2 to the k minus 1 over 2 to the k plus 1. Well, there we see that this is classic telescoping. And so what happens for a partial sum? So that is Sn will be equal to sum k equals 1 to infinity 1 over 2k minus 1 over 2k plus 1. So we're going to have that. But of course we're going to have this upper index is not infinity, it's n. And so let's expand out terms to just figure out what we're doing. So I'll have 1/2 minus 1 over 2 to the 1 plus 1. That's the first term in the sequence. So that'll be 4. And then I'll have plus, just like a telescoping sequence, I'll have 1/4, but then I have 2 to the next higher power, which will be 1 over 8. and then I subtract off 1 over 16, and this keeps on going all the way up to the nth term, which will be 1 over 2 to the n minus 1 over 2 to the n plus 1. So what happens to all these terms? Well, 1 over 4 will cancel out, 1 over 8 will cancel out, 1 over 16, all the way up to 1 over 2 to the n. It will cancel out with the previous term, which has the index k equals n minus 1. And so this will be equal to, this partial sum will be 1/2 minus 1 over 2 to the n plus 1. And now that we see this, our limit is easy. Well, this infinite sum is the limit of the partial sums as n approaches infinity. This, of course, goes to 0. And I'm left with just 1/2 at the end. Turns out it's just the very first term. Now, sometimes a telescoping series can be hiding. So for example, let's suppose you have sum k equals 1 to infinity, 1 over k times k plus 1. And so if we use our partial fractions, we can see that this is actually going to be equal to, if we expand things out, this will be 1 over k minus 1 over k plus 1. So the way to see that is that, well, what happens when I add these two together? Well, I have to have a common denominator of k over k plus 1. Well, k times k plus 1. I'll get a k plus 1 over here, and I'll subtract off the k, and I'll be left with just 1 in the numerator. Now this is telescoping again, and so what does a partial sum look like? Well, the k equals 1 entry is 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3, so on and so forth. And the nth term will be just 1 over n, which will cancel out, minus 1 over n plus 1. So the intervening terms all cancel out, and I'm left with just 1 minus 1 over n plus 1. And so I know that this will actually be 1 as n approaches infinity, because I know that this term will go to 0. And so I have this relatively complicated sequence, and I know that it has a limit. I can actually calculate it, and that is pretty interesting.